Hi, welcome back to the machine learning course. Previously, we saw a simple regression on a synthetic data, and when we run this code, we were able to fit a linear uh, model to our data. And I just added a new line here to calculate the correlation between the x and y, and I'm printing it here, and you can see that the correlation is 0.97, which is showing a very high correlation between x and y because the data is generated in that way. They're highly correlated, and and you can see that we have high R square score too. So that was what we did before, and now we want to see this was synthetic data, right? So we want to see like in a real data set, the data that is collected from real world, how the data look like, um, and how a linear model may fit such data. So for that, I have copied the same code that we have here for the simple regression, and I copied it here and here. Instead of um, generating the data based on a simple model, we are using a real data set. And here I'm just going quickly through the code to see how this data is fetched and what is the differences basically with the previous code. So here we are using the scikit-learn package, and we are using a built-in data set there for housing prices from the California state, and that this fetch California housing function, which we are importing here, is able to give us that data set very simply uh, with running this code. So California is our data set, and we are moving that data to a data frame, Panda data frame here. And here we are still doing the simple regression. So we have one target variable, one dependent variable, and one independent variable. Our dependent variable or target or y is the house values, which are recorded in this column in this data set, and they are of unit of 100,000. So we gonna times $200,000 to have a dollar value in the in our y. And and for the x, we are using this med inc, which is basically the average or median income for that neighborhood. So we want to predict the price of the house based on the average income of that neighborhood or segment. So we are so that's how we're gonna extract our uh, x and y from this data set, and the rest of the thing gonna be the same as previous code. So here we build the x and y, like x was uniformly generated between two values, and then y was created based on this function. Here, the x and y are given to us based on this data set. So that's how we build the x and y. The rest of the code is the same. Here I have some commented out code that I'm gonna use later. This is for filtering some of this data a little bit as needed. And again, I added the correlation uh, code here so we can calculate the correlation between the x and y before we start. And there is a little bit more changes here that because I want to add more figures to my plots, uh, I am using this grid of subplots instead of the just plotting the figures, and that's the only thing that I'm changing. I have a grid of 2 by 2, and I'm gonna have 3 figures later put in 3 of these spots. And so I'm gonna use the top part, the in that figure, the uh, top left spot, which is indicated by 00 as AX1, and this AX1 is gonna be my plot for the scatter of data. As you can see here, AX1, I do the scatter here, and I set the labels, and this is need to be changed. So this is basically uh, uh, okay. So that's house price. So that's the title, and the rest of the thing, as I said, is the same. We're gonna feed a linear model to it. We're gonna extract the coefficients and intercept from that linear model, and we're gonna plot that model, which is a line, a blue line, and we also gonna plot a horizontal line, dash the red for the mean of prices of the houses. And here um, we talked about it before. To evaluate the model, we have a few metrics: the MAE, mean absolute error, mean square error, and then I added a new one, which is basically the root of the previous one, root of mean square error, and uh, and then we have the R square metric, and we print them. And here I have a little bit more plots that I'm going to explain later, and then we show the figure. So now let's run this code, new code, which is showing the data from the California housing prices, and that is uh, the plot that we get now. So you can see that the red dots are the scatter of the prices. Y is the prices versus the median income. And the first thing that you gonna notice here is that the the scatter, the density of points are not as smooth as the the previous synthetic graph. In the previous one, I was uniformly spreading the x over the x-axis, but here you can see that there is a lot more denser than here. And also, it's although you can see there is a like trend upward for the prices as the median income increase, but it's not fully a linear uh, a linear relationship. And if we go to the metrics that we printed, first we start with the correlation, just correlation between y and x, and you can see that the correlation is at 0.68, is not as great as the previous example, which was at 97. This one is at 68. So you can see there is still a good correlation between these two numbers, but as it's not like a perfect correlation. And you can see also that we have uh, the the MAE and MSC. MSE. The MSE is hard to interpret, so that's why we have the RMSE. So so the MAE and RMSE are in the same unit as the Y. So for example, Y is the housing price, and we have the like average at 200,000 plus in that year. And the MAE is telling me that there is about $62,000 in average error between the blue estimator, my linear, and the reality and the ground truth. And and then if we look at the RMSE, that's even higher because the RMSE is affected more by the points that are further than the model because the square of error get more affected when the error is higher. So here is telling me that there is 83,000 in average uh, error between the model. These are not practical. This is not a practical model because like around this range of prices, uh, like even $5,000 is important for negotiation. So being off by $62,000 or $83,000 in average, it's a big deal and it's not reliable. But don't forget that here we are using just one feature, which is the median income. There is many more features in that data set, California data set, that each of them they might add a little bit more insight to the price. So as we include more features, the model can get more uh, accurate. That's one uh, side of the problem. The other side is that eventually the linear model might not be the model that we want to use here because um, yeah, the accuracy that we want to achieve by linear models might not be uh, the best or the most optimum here. So we need to look into other estimators uh, or other models for this data set. But just to show that what's the big difference between a synthetic data generated and a real data, and and you can see that like for example here in the real data at 500,000 there is there's a lot of points here and there is no point above the 500,000. This is indicates that the the house the when the price of houses was recorded here, like any price above 500,000 was recorded as 500,000. This is a this is a problem for this data set. So we already throw away a lot of information by doing this. So this can be misleading, these points here. So we can decide either keep them or remove them. And and to remove them, I can go back here and then I activate this filter. So I am saying here that if my Y are just create a mask for the Y less than 500,000 and we are only gonna uh, keep those. We're gonna keep the X and Y of those that the price are below 500,000. And then if you run it again, then now we get rid of those uh, those points that uh, you were at the 500,000. So each data set, when we look at the ground truth, we're gonna see this kind of things that need to be uh, pay attention to, and we need to prepare the data to make sense to be processed. One another thing that I wanted to mention here is that like if you look closely, you can see some bands here, and these are biased towards around prices. Like you can see this band is around 350,000. So people like to list their houses uh, like in a rounded number. So you can see like 340 is very little prices here, but for 350 there is a lot of like a cluster of points here. That is this is not the problem of data collection. This is just a human behavior that that is part of the ground truth. These bands are part of the ground truth. But uh, if we are interested in beyond that, in like the real value of the house beyond the human behavior, then we need to ask ourselves what is the real price of a house, right? How to define that if we remove the human factor? Because the price of a house is what a person willing to sell at that price and a person willing to buy at that price. And these two person, the buyer and seller, behavior can be affected by many factors, and they are all human. So so that question is a very critical question, and I don't even know if there is an answer to that. That beyond human behavior, if there is any like underlying real price of the house. But for this data set, when we are working with that, as far as are concerned, like we take these human behaviors as part of our ground truths, and we are not trying to remove those. So as I mentioned before, the in these new uh, plots that are from the real data, uh, the distribution of x and y are not as uniform and normal as the previous example that was from the synthetic data. And here I am adding these histograms to the x and y to plot these distributions across the x and across the y to see the differences uh, for ourselves. So let me run again, just adding two uh, two histograms. And as I said, like I have that figure with the grid, 2 by 2 grid. So now I'm adding the y histogram to 0, 1 and the x histogram to the 1 and 0. And this is the outcome. And you can see that like as I was mentioning, like uh, when the plot is like this, it means that there are some points that are around here, but they are very scattered with very low density. And you can see in the distribution of the how the median income is distributed. It is like around the tree, which is like 300,000, and it's skewed a little bit towards the right, but but above 10 is almost like no data points. So we need to decide, and if you want to like keep these areas or not, or we just want to focus on the areas that we have enough density to make our decision. And by making decision, I mean to have our model to be fit to the data. And and you can also see on the y-axis the how the how the points are distributed. The the median is around 150,000, and 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 as you can see from before, the average is around 200,000. So that's how the prices are skewed in the y-axis. Just to have a better understanding of our metrics, especially the MAE and RMSE, I mentioned before that this is telling me that in average, my error is around 56,000. Like whatever this blue line is predicting for my median income, uh, what gonna be the price? It's gonna be in average 56,000, which is around like this much off. This is based on the MAE, and then based on the RMSE is around 74,000 off. But when we are saying it's on average, like 56,000 off, which is here, this is the average, it means there is points that are less error and there are points that are with more error. That's how the average is standing here. So we should expect to have like errors like around 120,000 commonly, because the average is 56,000, so the errors are spread from 0 to 120. To have a better idea for that, I'm gonna draw the lines for MAE, for RMSE, and the double of them to see how this error margin is gonna cover our points. So for that, I just go to my plot and then I add a few more plots, and I add my model to MAE and minus it, and also add the doubles, and this is the result. You can see that this is my model. The dotted faded one is the MAE, so that's the average error, and then the dotted with blue color is like double of it, and you can see that most of these points are covered by the double MAE, which is like expected because the errors are from uh, 0 to, uh, if we consider the errors from 0 to double MAE, then the average gonna stand on MAE. But the problem with that is that these dotted lines, which are the absolute error, are not a good representative for these points. So these points are basically ignored, uh, but these are the very probable. These points are making a lot of problem because they are the one that are much further from the model. And and when we are using the square error, there will be a more penalty for these points, and and then the RMSE basically is greater than the MAE to to reflect more penalty for these points. That's why we have these dashed lines for the RMSE and double of RMSE, and you can see that they cover more areas. So they are indicating that the error we are encountering with this model is much more than the what mean absolute error is telling us. And you can see there is much more points that are covered by the RMSE. But in any way, there is no way to be able to account for all the points. But this is just in reality, RMSE is more accurately reflecting the reality because it's have more penalty on the further points. So it's gonna broaden our error and it's gonna bring down our expectation from the model. So it's good to see that for another feature of the California data set, that how that feature look like, the scatter and the modeling. And here I have chosen the average number of rooms that the house has, and is that a good predictor for the housing price? So I just change my X feature from the median income to average number of rooms here, and then I'm just gonna run it again. And as you can see that uh, for this uh, for this feature, the the distribution across the X is is very unbalanced. Like the number of rooms are like around five, mostly between 3 to 7, but we have data that are across this axis from 10 to 140 rooms. So to have a better look at this data, we need to get rid of these points that are maybe above 15. So let's go to the filter, and then we change our mask to X below 16, and then let's run it again. So now uh, we have a we have a better look at the distribution of the data. We have our X, uh, and we have our Y distribution. The X is more normal, like around 5, I would say, around 5 room, and then it has almost a nice normal distribution around 5, and the Y, like it's a bit skewed upward, but otherwise it's also look like a normal distribution. So this like distribution that is look like a ball, uh, this don't have usually any linear predictive uh, value. And if you look at the numbers here, the correlation is much lower than before, and the MAE increased to $86,000, and the RMSE 210,000. And you can see that the reflection of those numbers in the graph are widening these margins that we draw before to, and this is basically this model is like completely useless for predicting house prices because the margins of error are very wide. And the last metric that we can look at is the R square, which is at 8%, 9%, which is compared to previously, uh, which was 40 something percent for the median income. And for our synthetic data was above 90%. So we can see this has little. It still has some, like you can see that there is some like trend upward here, and that's how it's reflected here in the correlation. And the R square uh, uh, metric, it by itself is has no value, but maybe combination of this and the previous metric uh, can have a better uh, result for us. But as I said, uh, at some point when we look at all the features, we may we may see that the the number of features that have linear predictive values are not enough, and we might need to look into other models for modeling. But here we're just trying to explore the real data and to see the uh, to see for ourselves that the real data sets and the real ground truths are much harder to understand, uh, and usually they look like this, like a blob of points, and they are not like a nicely distributed across a line, and and therefore a linear regression, which is the simplest way of modeling uh, to build the estimator, it it only works for very obvious cases that there is a high correlation between the x and y, and sometimes when we have multiple feature, which we're gonna discuss later, the combination of a few feature can have a good linear representation of the target, but those are very rare cases. In uh, in reality, when we are dealing with the real data sets, usually we have things like this, that linear relationship is not obvious at all, and we need much more complex models to be able to model this kind of data. So before we finish, it's good to see uh, the error margins that we draw for the real data, and also uh, the histogram, the distribution of the across the x and y for our synthetic data too. So I have copied those line of code for our synthetic data too, and I'm gonna run this code, and now we can see that uh, for our synthetic data, the distributions across the x, because that's how we created the data, and it's like almost uniform from 0 to 3. That's how we generated. And then the y also has a uniform distribution. And then at the ends, this is because the line is finishing, and it's just the distribution of the noise, which is like a half normal distribution here, and then another half normal distribution here. And you can see that for the error margins, that, and we previously talked about it, that the MSE is sigma square, so the RMSE will be the sigma, and so basically, because this was a normal distribution for the noise, all the properties of a normal distribution and sigma can be seen here. So uh, so like almost 97% of the points are within the 2 sigma from the mean, and you can see this here, and probably only 3% of the points are outside this boundary, and the MAE also is within the inside the RMSE borders. Um, just last thing to see here uh, is to make our model and our data distributed horizontally. So we make our coefficient for data generation 0, and this will make our line, our model, and everything horizontal, and we're gonna get to a figure like this. As I said, the X distribution is uniform, but now the line is like just horizontally, and here I did that to see that when we do this, there is no variance uh, from the underlying truth, which is like A is equal 0, but there is variance because of the noise, and because this is horizontal, whatever you see here is just the noise, and you can see that we can almost see a perfect normal distribution here, and then uniform distribution here. And as I mentioned before, the RMSE is basically our sigma if it's a normal distribution. So this gonna put us at the sigma and 2 sigma here. So our sigma was uh, 0.5, and then mu is 1. So 1 sigma apart from the mu is 1.5, and then 2 is 2 sigma. This is completely matching our understanding from the normal distribution. And the 3% of points are above these 2 sigma.